Have you ever wondered why your hand feels warm near a burning candle or why an ice pack feels cold when activated? These everyday experiences are actually chemical changes and they all involve energy. In chemistry, every reaction is accompanied by an energy change. This is because bonds in the reacting substances are broken and new ones are formed in the products, and both processes involve energy. Breaking bonds requires energy input, while making new bonds releases energy. So, depending on how this balance plays out, the reaction either gives out energy or takes it in. We classify these into two broad categories: exothermic and endothermic reactions. For instance, when methane burns in oxygen, it gives carbon dioxide and water with heat. It's this release of energy that makes a flame hot. Energy change isn't just a lab topic, it drives everything from fireworks to digestion. Let's first explore exothermic reactions. These are the ones that release energy, mostly in the form of heat or light. They're the reason why burning coal warms your home or why respiration keeps your body functioning. When carbon reacts with oxygen to form carbon dioxide, it releases a great deal of heat. That's an exothermic reaction. Even neutralization, when an acid and base react, releases heat. Firecrackers, combustion engines, explosions all rely on exothermic reactions. And what's more, even your body breaking down food during cellular respiration is a form of controlled exothermic process. On the screen, you'll notice an energy profile diagram showing the reactants starting high and products ending lower, indicating energy release. That visual dip, that's heat being given off. Now imagine cracking an ice pack during an injury and feeling it get colder. That's chemistry at work, an endothermic reaction. These reactions absorb energy from the surroundings, usually in the form of heat, and that's why the container feels cold. A classic example is the thermal decomposition of calcium carbonate. The reaction is CaCO3 solid, that's calcium carbonate, breaks down into CaO solid or quicklime and CO2 gas. But this happens only when you heat it strongly. So, it's absorbing energy to proceed. Another great example is photosynthesis. Plants use sunlight to convert carbon dioxide and water into glucose and oxygen, an energy absorbing, endothermic process vital for life. As shown in the upward energy diagram on your screen, here the products have higher energy than the reactants, meaning energy has been absorbed. In chemistry, we often want to quantify the energy change in a reaction, and that's where the heat of reaction comes in, symbolized as delta H. The Greek letter delta stands for change and H stands for enthalpy or heat content. Delta H equals enthalpy of products minus enthalpy of reactants. If delta H is negative, energy has been released, that's an exothermic reaction. If delta H is positive, energy has been absorbed, an endothermic one. This is usually expressed in kilojoules per mole. Let's say during methane combustion, the delta H is minus 890 kilojoules per mole. That means 890 kilojoules of energy is released per mole of methane burned. These values help chemists predict energy needs or outputs of reactions, especially useful in designing safe, efficient processes. Here's a fascinating twist. Even reactions that release energy need a small push to get started. That push is called activation energy. It's like striking a match to light a fire. A little energy is needed to break the first bonds. Once that happens, the reaction takes off and releases energy. On your screen, observe the energy profile showing a small hump. That's the activation energy barrier. Reactants must cross it to transform into products. Catalysts help by lowering this barrier. They don't change the overall energy change but make the reaction faster. In industries, catalysts save both time and energy by reducing the activation energy needed to start a reaction. In many cases, it's important to represent the energy change directly in the chemical equation. These are called thermochemical equations. Take this exothermic example. Hydrogen gas plus chlorine gas gives two molecules of hydrogen chloride gas, releasing 184 kilojoules per mole. We write this as H2 gas plus Cl2 gas gives to HCl gas, delta H equals minus 184 kilojoules. The negative sign shows that energy is released. Now let's consider an endothermic one. Nitrogen gas plus oxygen gas gives two molecules of nitric oxide gas, absorbing 180.5 kilojoules per mole. That's N2 gas plus O2 gas gives to NO gas, delta H equals plus 180.5 kilojoules. These thermochemical equations are vital in energy planning, whether it's making fuels or designing cooling systems. So let's bring it all together. Every chemical reaction is more than just a rearrangement of atoms, it's an exchange of energy. Depending on whether energy is released or absorbed, reactions are exothermic or endothermic. We saw how heat of reaction, delta H, gives us a numeric handle on energy change. We learned that even reactions that release heat may need a kickstart called activation energy, and catalysts can lower this hurdle. We even wrote thermochemical equations that show energy changes right alongside the chemical formulas. From the fire in a matchstick to the fuel in a rocket, energy changes drive chemical reactions all around us. I hope this session helped you see how energy is the heartbeat of every chemical change, whether it's powering your body or fueling a factory. Remember, chemistry doesn't just happen in textbooks, it's happening in your kitchen, your cells, and your world. Catch you in the next topic with more incredible transformations.